So there's a number of ways we impair the signal to make sure it's going to emulate the performance that it'll see in a real environment. So can the receiver handle low amplitude signals? That's a receiver sensitivity test. Can the clock recovery track jitter on its input? That's a jitter tolerance test. Does the detector make the right decisions when the input signal is impaired? And that's an interference tolerance test. So there's ways, like I've been talking about, that we kind of close the eye, various ways to test these different receiver characteristics. So this is what a receiver sensitivity test looks like. We apply the test pattern, and sometimes it's a clean signal without timing impairments or jitters. Sometimes it has both, but you reduce the pattern generator output amplitude in steps, and then you continue, reduce, 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 reduce. Well, each time you step the amplitude down, you measure BER until you start to see errors. Jitter tolerance test, we apply the test pattern with the pattern generator. We leave the amplitude the same, but we apply calibrated amounts of sinusoidal jitter at one frequency and low deviation. Then it might have other jitters applied, but those are generally static during a jitter tolerance test. You change the amplitude and the frequency of the sinusoidal jitter, so that at that one frequency of SJ, you increase the deviation amplitude in steps, and you continue until bit errors are detected. Then you record the jitter amplitude where you got the bit errors, and you step to the next frequency. Usually you start low on the SJ frequency, and then you go to the next higher frequency and step and repeat. And then, I don't know if you can see it up here, but I think I have a JTOL on here right now where across the bird screen you see sinusoidal jitter amplitude, and at the low frequencies the clock recovery can track more sinusoidal jitter amplitude than at the high frequencies. And we have a little plot on that here. Oh, here it is, right here. So again, we start with a single tone of sinusoidal jitter. It's usually in the presence. We call it a cocktail of ISI, a static amount of ISI, a static amount of random jitter, and then sometimes there's bounded uncorrelated jitter or some other jitters. But the one you step is the sinusoidal jitter, and that plots the clock recovery characteristics. So on the margin test method, you put the receiver in loopback, and you start stepping. I don't know if he has automations on here, but this would be a template. So these would be the test limits, and so you'd start stepping your SJ amplitude up at this frequency, and hopefully your receiver would fail above this line. This line would be your pass-fail criteria. Oh, he does have animations. Oh, are they run by themselves? Sorry, these didn't run the exact same way last time I saw this. So anyway, the idea is you increase the amplitude until you get failures, then you step your frequency and you do it again, and you go all across this chart. And to speed up the testing, you may not need to test every single point when it's error-free and error-free and error-free and error-free and error-free. If you're testing each of these error-free points for a long time on the way up, maybe that's not the most efficient use of your time. So there's different search algorithms that you can change the jitter in different ways to speed up the test. There's a lot of tweaking on receiver tests to optimize the speed of test or the time of test. And if you have any trouble with that, we have applications engineers that can help you optimize that. But there's different kinds of algorithms: linear log, binary weighted. So a binary would be, put half the instrument's jitter out. Is it making errors? If no, then go to 3/4. And do a binary search that way. And that can more quickly converge on the answer. You might do a top-down search at low jitter frequencies because you're really sure, or pretty darn sure, that your clock recovery can track out all of the low frequency jitters. So you just test the worst case first. If it passes, you don't have to test any of those lower points. So the point of this is, though, if doing a top-down versus a bottoms-up search can give you different results, particularly with clock recovery, because clock recovery PLLs, if they start from a locked condition, they can withstand more jitter than if they start from an unlocked condition. So if you start unlocked, it might take a longer time to lock, and you'll get a result down here, where if you start locked and sneak up on the BER limit, you can get a better performance. Interference tolerance testing is adding amplitude noise. So jitter closes the eye in the time direction. Amplitude noise closes the eye in the voltage direction. So basically you impair it with noise riding on top of the data signal. It's either sinusoidal or random noise, and it can be either common mode or differential mode. Basically, for interference tolerance testing, you start at a low amplitude. Darn it, I keep jumping the gun on these automations. And then increase the noise until you start making bit errors.